All right. Well, Happy New Year, everyone. Welcome to the Winter Quarter CDM Research Colloquium series, and thank you all for being here today. For the first seminar for this quarter, it's my great pleasure to introduce Dr. Pratool Bharti, who is an assistant professor in the Department of Computer Science at Northern Illinois University, DePaul, Illinois. Dr. Bharti holds a bachelor's degree in computer science and engineering from India, and a PhD also in computer science and engineering from University of South Florida, Tampa, Florida. Prior to joining NIU, he was working as a research and development manager at an AI and computer vision-based startup. Dr. Bharti's primary research interests include context-aware sensor fusion, computer vision and neural networks, embedded machine learning, and artificial intelligence algorithms. Currently, his research lab is developing and leveraging pervasive technologies to improve the public and personalized health and well-being. He is also interested in intelligent transportation systems, mobile computing, and wearable technologies. I'm glad to have Dr. Bharti at our colloquium to share his research work today. The title of his talk is Context-Aware Machine Learning Models for Personalized and Public Health. Welcome again. Thanks for being here today, and please take it away.
Thank you. Thank you so much, Thiru, for inviting me for the talk and also giving a very generous introduction. So thank you, everyone, and welcome. As Thiru said, I'm Pratool, assistant professor in computer science at Northern Illinois University. So my primary research interest in generating and developing AI applications which are useful for personalized and public health. And today's talk is also involved this personalized and public health and how the context-aware machine learning models work for them. So with that, let me start the presentation. One second. Yeah. So I have divided the today's presentation in two parts. One is the personalized health and another is public health. And I will discuss two topics within both. So in the personalized health, first I will go with complex activity recognition with multi-modal, multi-positional body sensing. As you have seen with Apple and the Android watch, like a lot of sensors are embedded within that, and how we can exploit those sensors to figure out what activity person is doing. And the second would be estimation of walking and running speed using wrist-worn wearables. We are already doing a very accurate walking and running speed with the GPS, but a lot of time our GPS doesn't work, especially when you are walking on the treadmill or walking indoors. Then how we can use our accelerometer and the gyroscope embedded within wrist-worn wearables to detect our walking and running speed accurately. And not only it will help in speed detection, but it also help how much calorie we are burning during any exercise session. And then I will come to the public health. And in the public health also, I will discuss my two recent work. First is how we can classify mosquito species, because mosquitoes, not all mosquitoes are equally harmful. Some of them are very harmful, which is responsible for Zika or dengue and malaria, and some of them are non-harmful or harmless, I should say that. So it's very important to identify which mosquitoes are in our neighborhood so that we can take the appropriate action. So in that realm, I will discuss how we can leverage our smartphone cameras and image processing techniques to classify mosquito species and understand our environment around. And then in the second public health application, I will talk about how we can estimate water level in a running stream using computer vision and machine learning to design a early flood warning system. So with that, let's start with me asking a question. So the first topic would be the context-based human activity recognition using wrist-worn wearables or our Fitbit or Apple Watch. So in this question, I would ask, is just knowing the physical activity enough? Because all of these variables can tell us how much you have taken steps or what you are doing, what exercise you are doing, or in general, very high level activity. But the question is this the very useful? Is just knowing the physical activity enough? If somebody is telling me, suppose I want to track my elder parents in India, and suddenly I get a message that my parents are lying down, is that just good enough? And the answer would be not very good enough. Because if you see that lying down on a hospital bed and the lying down on a kitchen floor after sleep, both are basically lying down activity. But if you add some more context on it, one is pretty usual. Like I see that on the left-hand side, person is in the hospital care, but on the right-hand side, person needs an immediate attention because she has been falling down. So what I am trying to see that just only the activity without giving more context to it is not very helpful and is not very useful. But if you can tell that in the left-hand side, the person is lying down in a hospital bed under care versus the right-hand side, person is lying down because he had slipped or fallen through or passed out. So that may be more context, and that what I'm going to discuss, like how to add more context to the situation and then make our activity recognition system more useful and more effective. So why we need activity recognition and how we can support it. So just a little bit background about it. Already in 2017, that's the latest data I could get from the CDC, 8.5 million seniors in USA required some form of assistive care in 2017. But they are also saying that in very near future, every 1 in 5 seniors or in every 1 in 5 person in the US may need some form of assistive care, either disability care or elderly care or due to some mental health issues. But 80% of these over 65 are living with at least one chronic disease. And also every 69 seconds, someone in USA developed Alzheimer's disease. So the idea is we need to come up with some sort of cost-effective assistive technology, which is very affordable, but also very effective to help people who needs assistive care. Because staying in the nursing home for longer period of time is not cost effective and not affordable for larger population. And also you see that just to marry the two thoughts, one is that assistive care, everybody or like a large portion of the population need assistive care either today or in the near future, but also that wearables are getting cheaper and cheaper every year. So in 2021 alone, 200 million wearables will be shipped globally, and 35% of all wearable consumers are in USA. And smartwatches and fitness trackers are one of the most popular wearables. And not only they are capable of telling you your heart rate or your daily activity, they also come with very powerful CPU where we can process those sensory data to analyze in real time what kind of activity going on. So the idea is how we can use these wearables or the wearable sensors to design human activity recognition system to track the person or basically to monitor them whenever they need assistance. So activities can happen in two levels. One is the atomic activities, which is very simple: running, walking, standing, walking downstairs, walking upstairs. Those are important to know because that's where you know that if your elder parents are taking care of their health or not, they are doing exercise or they are moving well or not. And some of them are health related, like for the Alzheimer's, people are forgetful. So they go indoor to outdoor and outdoor to indoor pretty often without knowing where to go. But also complex activity, like in emergency, if the person is lying on floor, lying on sofa, if they are trying some harmful activities like hanging, injecting, or if they are cooking every day or not, or regularly or not, if they are sitting too long on the commode, if they are socialized or watching TV or not, kind of the mental health, and also how much using bathroom sink to make sure that if they are following the proper cleanliness protocols or not. So the idea is atomic activities are those which is very simple, cannot be broken into more simpler activities, and the complex activities which is combined by one or more atomic activities. So the idea is if we already can detect using the sensors, what are the contexts we need to identify more importance or more context to it? So for an example, many fine-grained activities are similar, but they can happen in the different context, making them very different interpretation. So for an example, I already took one example, but a lot of those context information can come from different sensors, which can be present in either in your home or in your wearable. So for an example, location. We think that location is not important for the activity, but if somebody says you, I'm driving a car, then I don't need to tell you that I'm playing football or I'm running, because if I'm driving a car, pretty much my limitation, my activities are limited inside the car. And also if I say I'm in the bathroom, I'm in the washroom, I'm in the bedroom, so with that, my domain of activities gets pretty limited. So the location is one of the very important context in activity recognition, even though it doesn't give you very fine-grained information, but it gives you a lot of important information. And the same with humidity and the light intensity. Believe it or not, in your house, every corner of the house has a different level of humidity. In your bathroom, in your kitchen, you have different level of humidity compared to the bedroom. So without putting a GPS or a location sensor, by humidity also, we can pretty much know what part of house we are in. Same with the light intensity, the pressure. Pressure can tell you if you are going upstairs or downstairs, because we know that going away from the earth decreases the pressure, and towards the, like with the height, pressure changes. So if you have the pressure sensor in your phone or in your wearables, you can understand if you are taking left, going upstairs or downstairs. Temperature can help if you are outdoor or indoor, especially in Chicago or in Illinois or cold area. And not only that, it also temperature sensor can help if you are cooking or not, because if you are cooking, if you are wearable and you are moving your hand uh, near the stove or near the fridge, it can give you a lot of information. If your temperature is not stable, that means you are cooking, and the same with the light intensity. So the idea in this is, what I'm trying to propose is, yes, activity recognition had exploited the accelerometer and the gyroscope sensor, which gives you the real-time response of how your hand is moving. But just hand movement is not enough to give the correct information with the correct context. So that's why we need, other than accelerometer and the gyroscope, we need what kind of environment we are in, what kind of location we are in, to fuse this information to give the better context and give the better idea. And in this context, in this realm, I will give you my first research thrust, how to do this in-home complex activity recognition by fusing accelerometer, gyroscope, temperature, pressure, humidity, and the Bluetooth beacon signal, combining to give the better activity recognition. So the problem statement is, recognize in-home complex human activity having similar signature, but vital contextual difference, like sitting in sofa versus sitting in bed versus sitting in commode, and lying down in kitchen floor versus lying down on bed. And also how we can combine the decision, how we can use the multiple variables and then combine the decisions to come up with the final one. So the approach is, first collect the quality data and process them, make sure that they are noise-free, error-free, get the good features to understand that we capture the correct patterns out of it, and then design machine learning algorithms which can recognize those patterns automatically, and then we will discuss the results. So in the right-hand side, you see that in the top, we are taking all those sensory data we have discussed so far. and then what kind of window we need, either 1 second window or 2 second window, how much information we need so that we can understand what kind of activity person is doing. And then we will see how the probability based conditional random field model we have designed, and how the different variables at the different body parts can also help to get the better idea. So very briefly, the data collection for this, we used a simmer sensor. I will talk about more the simmer sensor later, but as you can see, the simmer sensor is more like a tiny small sensor which you can tie anywhere on your body using any tape or with any adhesive. And it has a lot of sensor, and especially they have accelerometer and the gyroscope and humidity, pressure, and temperature. They don't have the light, but we can also add any other sensor we want. It's more like a plug and play sensing platform where they say a lot of different kind of sensors which you can directly plug in them and get the data from it. So we also generated a smartphone application which can directly sense the data from these sensing applications, sensing devices. And also we deployed Bluetooth beacons at the different part of location to make sure that we understand where the person is. So a lot of work has been done in this field using the wearable sensors like belt clip accelerometer and the smartphone accelerometer and the video camera. But we are the first one where we had explored other kind of environmental sensors and the location within the house to see how can we do this fine-grained complex activity classification. So in this, you see that this is the kind of our important accelerometer and the gyroscope, pressure, temperature, and the humidity. So the first column, you see that the sensor name is there, and the row, you see the numbers basically depend what activity person is doing. So if you see that the 1, 5, 9, 11 person is standing on downstairs, upstairs, walking upstairs, downstairs, cleaning utensils, refrigerator, and the cooking. So the idea is definitely if you see the accelerometer and the gyroscope, they are very sensitive towards your hand movement. If you move your hand, they will change their value. And accelerometer basically records your hand acceleration, means change in velocity with respect to time. And gyroscope changes the rotation of your hand. So that is more like angle per second. Pressure, as we discussed already, it changes how much atmospheric pressure we have at that any particular level, and temperature and humidity is self-explanatory. So the idea, you see that the pressure changes in 2, 4, and 6, and you see that if the person is taking upstairs or downstairs, how the pressure is changing rapidly compared to the 9, 10, 11, 12 when person is on the same floor. So we don't need even activity and the gyroscope by just looking at, because if you are just walking or you are taking stairs, accelerometer data or the gyroscope data doesn't have too much difference. But if you combine with the pressure, it's very easy to understand if the person is normally walking on the same floor or if the person is taking the upstairs or the downstairs. Same with the temperature and the humidity. If you see the number 12 and the number 13 on the row side, you see that 12 is using refrigerator and the 30 is in cleaning utensils. So if your faucet is on, or if you are using refrigerator too often, the temperature and the humidity changes a lot, where you can understand that we are using fridge or we are in the kitchen. So once we combine all this information and try to design a pattern recognition or AI algorithm, we can easily understand more information than just the hand movement or the hand posture, because activity is much more information than just tracking the hand or the body movement. So what we did in this, so we first designed any AI or supervised machine learning algorithm needs some training data. So basically we simulated the data by asking our lab mates and students to collect these data. And what we did then, we segmented the data in different chunks, like 2 seconds, 3 seconds, just to make sure that we don't want too long data, too long window, so that each window can have 1 or 2 more than one activity so that it's noisy, or we don't want to interrupt the activity too early so that we don't have any clue what activity is going on. So for an example, if you are trying to detect the cooking, just 1/4 of second may be not enough to understand if the person is cooking or not. So segmentation means just try to plug and play for what activities we need longer time or the shorter time. And then the feature extraction is basically try to identify how those signals are behaving so that we can find some useful, important signals or statistical features. So for an example, one can be how much variance in the accelerometer data, or how much your entropy is changing, or how much your mean is going up and down a person is doing one activity versus another. So in the starting, we do a lot of different features based on the visualization. And then we select some important features, which is not only we believe are good, but also good for our accuracy. And once we decided with our features, we trained a conditional random field algorithm. So what is the CRF is basically, this is a probabilistic based model, and they use the sequence. So sequence means they're not only taking the present sensory information, but also take what was happening in the last window. So for an example, if the last window person was walking, they will also put a lot of weight on the last window. And if the current window, we are taking the sensor. So two information we are taking. So if you see here, so the whole idea is trying to get this posterior. So X is our feature from sensory data, and Y is our final activity selection. So getting this X, we want to find the probability of Y. So suppose if we are trying to track the 20 activities, so for each window, this model will give the probability of each activity, and whichever activity has the highest probability, that will be the final activity. But if you'll see here, we are aggregating two things here. So one thing, you see that we are trying to do the X and YT, means what is the current Y for the current X, but also the second part, you see that we are modeling X, YT and YT minus 1, means for detecting the YT, we are saying what was the previous timestamp activity, what is the current sensory data, and then by adding both, we are trying to finalize the current activity. So very quickly, in the feature selection, we took both approach, the Shannon's entropy information measure, but also the Euclidean distance measure. And by using both approach, we decided the sequential modeling of activity data, where you see that YT is activity at the time t, and XT is the sensory data at time t. But YT is connected with YT minus 1 and XT. So both these informations are responsible to give you the current information of what activity person is doing. So YT to YT1 is basically transition functions your algorithm learns, but XT to YT is basically a state function, how the features are correlated with the final activity. So once we have all this information, we calculate the posterior probability of PY given X, and all these lambda n and the GM and the mu m, all these informations are basically trained or learned during the training process. And then we select the top K activities based on the conditional probability. And also what we do, based on all top 3, we detect that which one of them is the final activity. So that was from the each position. But now we come to see that not only each position, but now we have 4 different positions. And then according to talking to many physiological experts, we also see that the wrist is important for these activity, thigh position is important for these activity. So how we are taking the decision from the 4 variables put on the different part of the body, and if there is a collision happens, suppose that if the thigh is saying some different activity and the hand is saying some different activity, how we can change or how we can come up with the final decision, That's what we come up with, is which application or the which part of body is important for what kind of application for the tiebreaker. And then we did two kind of validation. One is the same user tenfold cross validation. Same user means we did train on one user at one part of time, and then we collected the data at another part of time to see that if we are just taking the same person data for training and the same person data for testing, what is the accuracy? This was a pretty simple test because the person usually walks the same way or does the activity same way. So out of all the 19 activities, we had 98%. So what we did that we collected for all 10 users, and then we did the average performance, and it was 98%. But what we also did, we did the cross users, this leave one out performance, where that we left one user out, and then we only used other 9 users for the training, and then we average out all the users. So in that, we had little less accuracy, but this was still fairly good. So the idea, just I want to conclude at this particular work, is that context-based sensory data fusion is very vital for ADL recognition, because a lot of time people just take the data and try to design their algorithm to see which algorithm is fine, which algorithm is giving you the better accuracy. But most of the time your data is the crucial part, not the algorithm. So if your data is as clear as day and night, no matter what simple algorithm you apply, you still get very good accuracy. But if your data is noisy, pretty much almost all algorithm will give you very shaky result. So instead of putting a lot of information on algorithm, a lot of effort on algorithm design, if we put more effort on getting the cleaner data, the vital data, I think that will be giving us more important or more accurate ADL recognition. And ADL is activity of daily livings, like walking, running, or for. And second part is very important future work for us is how we can implement optimized AI algorithms or the lightweight AI algorithms on the sensing device itself, so that we can develop a lot more assistive care applications, which is useful for personal health. Because most of the time, if you want to track a person all the time, your device doesn't have enough resources to continuously run an algorithm and give you the results. So for that, we need to find some ways, some optimization of algorithms, which can allow us to continuously run our algorithm and give us the better idea of what's going on. In the same context, in the same domain, I will also give you my second work idea about how we can detect the speed of the person, like walking and running speed, using just the wrist-worn accelerometer and the gyroscope data. So why this is important? So the motivation is, whenever we do any walking exercise or any exercise session, we are really interested to know how much energy we have burned, how much calories we have burned, because we want to know that if today we have burned enough or the same with the yesterday or the less than yesterday, because that is really important if somebody is more conscious about their health or they are trying to lose their weight. So planning their exercise session or counting their calories is really important. But that is not possible if there is no assistance or there is no technological help for you to do. And to do that, you need to be really make sure that you count very precisely, very accurately your exercise. So for an example, if you are walking and running, how fast you run, it's really important to know with how long you are running or how much time you are running. So the speed and the time both are important. And also existing solutions are mostly based on GPS that are energy efficient because they are continuously communicating with the satellites. And also they don't work well in indoors. And also if you are having a treadmill. So your GPS won't work if you are walking on treadmills, or your GPS won't work if you are just taking round and round in a small portion of some indoor sections. So some of the most accurate devices in the market, they are not very pervasive, means they are not very comfortably utilized. Like you can see on the bottom side of this, like they are either utilized on the foot or they are coming on the chest mounted sensor. So our idea is how we can use this existing commercial watches or like any hand worn on the wrist worn devices using just the accelerometer and the gyroscope to detect what is the exact speed of the person, whether the person is walking or running on the treadmill or the outdoors, it doesn't matter. So some quick information in this regard, people track step counts to estimate the amount of calories burned in a session. And also the past research shows that the 10,000 steps per day helps overweight adults to lose weight. But the problem is, are the 10,000 steps enough? Means, are just counting the steps enough? And with this question, I will also give you the two different research work findings. So for an example, no matter how many steps you are taking, for an example, let's take that if you took the same steps with a different running speed, you are burning very different calories. So for an example here, if you are running at 3 miles per hour versus running at 5 miles per hour, but if you have run for the same distance, your calorie burn would be 1.5 times more if you're running at 5 versus 3. So that means your step counts is not very good indicator of how much you are working compared to, because you need speed also, and also you need to know that what time you are working. And the same with the walking, 1.25 versus 2.5 on the same distance, you are burning a lot more calories. So the idea is how we can use this small little devices, which is present in almost all of the smart wearable sensors today. But we use a little bit more sophisticated sensors because we wanted to do a lot more research in this. So this similar device is very popular in research community. They have a lot of sensors in it, but we basically use accelerometer and the gyroscope. They have Bluetooth, so we can directly transfer the data in the real time to our phone or laptop. We use 50 samples per second for the sampling rate. And we did real-time processing on the real-time live data so that we can tell the person in the real time what is their current speed. So this is one of my students. We collected the data on the treadmills because it was very easy to collect the ground truth of the person, what speed they are working. And you see the person had tied these small devices on the wrist, and another person was guiding them like run at this speed, that speed. So this is kind of a data collection protocol we have. We had 15 participants, few males and few females, different speed range 3 to 7. Every person was giving 9 to 16 session, and session means one speed was one session. And for each speed, they had to walk or run for 45 seconds. Total, we had 205 sessions or data of 9,225 seconds, and sampling frequency was 50 hertz. So that means 9,225 into 50 data point. So the idea why we thought that we can do this without GPS, it comes from this slide actually. Because if you see the top slide, which is the top row, which is accelerometer sensor, walking at 3 miles and the running at 7 miles, both have very huge difference. The first difference is you see the cycles are happening more closely at running at 7 miles per hour because the hands are moving very synchronized way with the legs. And also we have more frequency in the 7 compared to 3. So the idea was we have very unique pattern at 7 versus 3. So it's possible that if we can just utilize this pattern, we can detect what speed person was running. And the similar pattern you see on the gyroscope side as well. So how to count the speed? So speed is step length into step frequency. So like if you want to know what speed person is walking or running, you need to know what is the length of every step and also how frequently they are taking that step. And we need to count both to come up with the final step. So the step frequency was pretty easy because we used the Fourier transformation on the signal. So it was easily giving us what is the frequency of our hand movement. And since hand and legs move in the pretty synchronized way, so we also know that how many steps person are taking in every second. So the the step frequency was very easy to know, but the challenge was So one quick thing here. So one thing we saw with the step frequency is we thought initially that, okay, people are taking almost equal kind of step length, like the stride length. All they do, they change their frequency. For an example, if I'm running at 4 versus if I'm running at 8 miles per hour, my step length would be same. All I will do will take more steps. But that was not true here, because if you see, we took the 3-person, one with the 156 centimeter, 171, 177. So if you see after 4.5 or something, people starts running because it's not possible for a person to keep walking at the 4.5 or 5. So even they increase their speed, their frequency didn't increase, means they were still taking the same number of steps. So that means if the steps were not increasing every second, step frequency means how many steps you are taking every second. So if the step frequency was not increasing, that means their step length was increasing. So that means if the person were increasing their speed, the length of step was increasing longer and longer, and their frequency was the same. So that means we need to find out how their length is increasing with the help of just the hand. Because remember, our watch is, or our smartwatch is on the hand, not on the legs. But somehow we need to figure out how the legs steps, or how the step length or the stride length is changing. So that was a challenge here. And other challenge was that, especially at the lower speed, people were free to do anything. So suppose if you're walking at 2.5 or 3 or 3.5, you are pretty comfortable, and then you start using your smartphones and start talking to the person. So your data becomes a lot noisy, and it becomes so hard to find the pattern in that. But the higher the speed, like 5 or 6 or 6.5, then you don't become comfortable to doing whatever you want. And then it's very easy to find a unique pattern or the common pattern in your data. So the higher speed, we were more accurate. In the lower speed, we were less accurate. And that all because of the person's hand were moving very differently. So what we did, we tried a lot to do the length detection or the stride length detection using the machine learning approach, and we couldn't find much help. And that's what we tried, like whole holistic approach that just take all the sensory data and directly try to do, instead of try to find the frequency and the step length, we try to find, can we directly detect the speed. So this is the whole idea we had. So we will take both accelerometer and the gyroscope separately. So we won't merge them in the beginning. And then we apply the neural network with the convolution filters. We take the 27 filters initially, and then we increase our filters as we go down the layer in neural network. And then we apply the max pooling. And after the max pooling, we concatenate both accelerometer and the gyroscope. And in the end, we apply the fully connected layer. And with this, we try to find a final regression layer, which will give the real-time value of the speed. And we evaluate against 3 matrices: mean absolute error, which is like what was the ground truth versus what is the correct, what is the prediction. And one is the percentage error, and third is the R square. And we also did the trend test evaluation and the leave one out participant evaluation. So if you see the speed detection with the all participant trend test splits versus the leave one out here. So it was very accurate if we didn't just combine all the users' data and then they divided the trend data and the test data. So we see that all the data points are pretty much diagonally, means the true speed and the predicted speed are pretty much same. But if you did the leave one out participant, means we left out one participant for the test and used all other participants for training, we see that the data were not very accurate here. And interestingly, the data were more lousy, or the algorithm was not very good on the lower as well as the very higher speed. So what we found here, that lower speed also people are using their hand in the very random way. So it's very hard to find a unique pattern. But also on the higher speed, we found that some persons are moving their hand too much. Some persons are not moving their hand too much. So it was very unique from person to person. So that's what. And another thing that very few people basically did the very high speed experiment. So we also found that maybe that can be the reason that our model was not very accurate at the higher and at the lower side. But in the left-hand side, you see that MAPE. So our trend test split, our average accuracy error rate was less than 4%. And the RR2 score was like more than 0.8 here, more than 0.6 here. So that was a really good, and we also had a demo where we saw that how we can real time. So we used to see that if we change the treadmill speed, our algorithm was also able to detect gradually if the person is changing the speed in the treadmill. So that was really a good experiment from the research perspective. But for the future work, we want to make it more practical and more applicable for the real life purpose. So we wanted to propose this system for the less privacy invasive, and also how we can employ this on the commercial watch and use this algorithm to detect in the real time. Now we have 10 more minutes, but let me quickly go through my second research thrust, which is computer vision and participatory sensing to surveillance of disease-carrying mosquitoes for public health. As I said in the earlier, not all mosquitoes are equally dangerous. Some of mosquitoes, especially with the responsible for Zika, malaria, and dengue, but 90% mosquitoes are not deadly. So for that means, and especially even in the male versus female, only the female mosquitoes carry this disease vector. And also in the female mosquito vectors, not all of them can carry this disease vector. So very quickly, there are 4,500 species across 41 genera, but only the Aedes, Anopheles, and Culex are the deadliest vectors, and other 38 are not so. So surveillance is very critical to understand how to identify which kind of vectors are around our community, around our houses, but the experts are very few. So we collected this data in Tampa, in Florida, and where we have dedicated personnel from Mosquito Control Board, which lay traps in mosquitoes for area and then bring those mosquitoes and identify them. First, they put them in the freezer so that they die there. And then next day, they try to identify manually under the microscope which mosquitoes are prevalent in the area. So what we thought, instead of bringing this manually, collect the mosquitoes and then identify them by bringing them into the Mosquito Control Board office, why not, if we can bring that expertise to the person so that any person can take the mosquito's picture, obviously the died mosquito picture, and then can we identify them by just taking the picture. So the whole idea was how we can train a algorithm which can just identify that which species that is, with the Aedes or Anopheles, and basically that will help the Mosquito Control Board with the load sharing, but also identifying very quickly which kind of area has what kind of disease are growing. So this is the data collection part. We collected a lot of mosquitoes from different parts of Tampa using the help of Mosquito Control Board and the Hillsborough County. And we started with Aedes, because the Aedes aegypti, where that time the Zika was growing rapidly. So Aedes aegypti was the mosquito which were responsible for Zika, but also Anopheles, which is for dengue. So we had the Aedes mosquito, Anopheles, and then some of the more general mosquito, which is not responsible for any dangerous diseases. But the technical challenges was mosquitoes look pretty much same. Even though we worked more than 1 year, still we were not very qualified enough to identify different mosquitoes, because they are pretty much look very same. So they have very low interclass variability. And also the different mosquito species have identified at different body location. It's not like human, that each human has a different face pretty much. Some mosquitoes legs having different, some mosquitoes body has different patterns, some mosquitoes have their flies has different patterns, like their wings have different patterns. So it was very hard for the mosquito to identify differently. So as we say that Aedes teniocrincus and Aedes aegypti had the legs differently, but the Anopheles crucian and the culex had the very dark black abdomen and the dark light white lateral patches. So our first approach was very simple. Just take the mosquito picture, remove the background, do the background segmentation. And once we do the background segmentation, apply some dimensionality reduction so that we have very less pixels to work with, and then do some clustering saying that which two images look same, and then simple do the support vector machine to predict that what kind of species. So the idea was only collect those pixels which has the mosquitoes. So do the first mosquito classification, remove the background. And once we have the mosquito pixels, just try to identify how many colors are there. So how many the brown patches are there, how many black and white patches are there. So based on those clustering, we were trying to identify if we can do the better job. So interestingly, out of this 8, we did the 71% accurate prediction for the 10-fold cross validation for the whole precision recall and F1 measure. But that was not good enough. So what we wanted to do, okay, so we know that anatomy is different. So we divided into 4 or 5 anatomy. Like first we disintegrated each mosquito pictures into 5 parts. So this is the leg part. This is, as you see in the middle part. So where is the legs? Where is the mouth? Where is the wings? And where is the abdomen? So 4 parts we divided, and then each part we tried to train a different machine learning algorithm. And once the decision was there, then we combined them into the final part. And you see this was the anatomy segmentation. We take the full picture, divided them into different anatomy, and then train a different neural net classifier on each thorax, abdomen, legs, and wings. And then tried a logistic regression classifier to figure out what is happening. And also we tried an activation map just to make sure that our algorithm are learning the proper things and they are focusing on mosquitoes instead of just the background. And here we got much better results. Instead of 71%, now our accuracy was 88% overall. And as you can see that, and we also did not only the species classification, but also did the genus wide, like what is the Aedes prediction or the Anopheles or the Culex. So third approach we did, like instead of again doing this classification on anatomy based, why not if we do this, the whole holistic approach, just take the full image, don't do anything, and train a more complex neural network, which will give you the direct result of the species. And we are still working on it, and we don't have any results to share right now. But very quickly, in the end, I will share my third thing, which I said that early flood detection system using computer vision and machine learning, using simple vision approach. So this was the automated method for detecting water level using computer vision and machine learning. Needless to say, flood is a natural disaster. More than 1 billion lives affected worldwide in the past 20 years. $1.6 billion worth of revenue loss in USA in 2018 alone. And the worldwide itself, it's a big problem. And you see that from 95 to 2009, how many people lost their lives from the flood. And especially the urban flooding is one of the biggest problem from the lives wise, but also from the revenue wise. So what is the current existing system? Current existing system, as you can see that a lot of people or USGS, like USGS department in USA, they install a lot of meters like the gauge, and then they try to see what is the water length, what is the water height or the depth of river every 15 minutes, and then they record it. But our approach was more like vision approach. Can we directly install a camera on the pole near the river, and can we detect the water level every minute so that we don't need a gauge or any installation infrastructure to install in the river, and make sure that we maintain them. So this is the AOT model, and this has just a small camera in it. And we have a Wi-Fi module and the Bluetooth, which we can directly import our images every minute. And this is, you see that one of the view of our NIU campus. And this camera was just taking this picture. And idea was, if you can see, if you can detect the length of this bridge pier, basically that will give us the height of water at any particular time. So we tried our approach. We first tried with the color image, but the color image had a very different intensity based on day, night, rainy. So it was very hard to identify that where is the edge of the water, because unless we know the edge of the water, where the water meets this bridge pier, we cannot detect the length. So for that, we first removed this color with this edge map. So you see that in the left-hand side, we have input color image, but on the right-hand side, we have this edge map from the HED. I will tell you what is the HED. HED was very sophisticated and the latest edge detection algorithm, which takes the color image and gives you all the edge maps, like where the edges are. So now it became very easy for us compared to the left image. The right image, we already know where the water meeting the bridge. And then all we need to do is find that where is this line and then find the height. So that's the idea we did. So from this HED image, the edge map image, we first figure out how the bridge looks. So we identify a template, we did the template search. And once this template is found, all we need to do, just try to identify all those pixels where the water level is approaching. And once this water level is found, we detected for this picture, this is the template image found. We went from the bottom to top and then identify where the pixel value is suddenly increasing with the 70th percentile. And we found 70th percentile with just hit and trial and going through a lot of images. And you see this red dots where we see that the significant value of pixel is jumping. And once we have this all blue pixels, red pixels, then we just trained a logistic regression, a linear line algorithm to find out where is this bottom edge. Even then we had a lot of problem because sometimes images were noisy, and this is where our pixels were finding out. You see here, here, and here. So then what we did, we trained a closest line approach using the logistic regression, and this dots, first we trained this line and we already knew where is the template. So basically idea was just find the difference in those lines to detect what is the water level. And this is the whole our algorithmic flow. So take the input image, get the HED, find the template. Once the template is find the water coordinates. And once the coordinates is find the water line. And once the water line is find what is the reference water line position and what is the current water line position, and then find the difference in two parallel lines. So to train this, we collected a lot of ground truth and the bridge height. Not to train, basically, just to find the results. And again, here we did all three calculations: root mean square, R square, and mean absolute. And we see that our algorithm error was 4.3 pixels for the root mean square, 95% accurate with R square, and mean absolute error was 3.5 pixels. So the correct position versus predicted position were only 3 pixels different. And this is the error from the 2 months of the data. And you see there is a gap because in the night it was not working, only it was working in the daytime. That's why you see there is a gap between these clusters. And almost every time the error was close to 0 and within -10 to 10 pixels. So the challenges were like computing ground truth were very difficult because it was manual. And another challenge was there was still a lot of problems. So that like one time, this is the image, you see that a shadow of the tree is on the bridge pier. So there is no way we can see how the water is flowing inside the bridge. So the future work is we can deploy more sophisticated deep neural networks, especially the object detection technique, to identify where is the bridge, and then we can find the water level. So in the end, to summarize, what is the future direction and the conclusion? We need more trustworthy and explainable AI. for healthcare application, because it's very important now to convince end users to trust the user, and that convincing power, that trustworthiness should come from the application design. Second thing is cost-effective pervasive system is required for personalized and public health, like how we can design more cheaper hardware so that the cost of pervasive system goes down. And the third is how we can effectively fuse our data, optimize our model, and compress our system so that it can deploy real time on the sensing devices itself. So that's the end of presentation. If you have any questions, I would be happy to answer. Thank you.
Thank you so much, Pratul. It was really good.
Thanks. I think I lot a little bit longer than I thought, but
no worries. No worries. That's totally fine. Any questions from the audience?
Hi, can I ask a couple of questions? This is Nandini here. I'm sorry, I don't have my video on.
Yeah, no problem.
First of all, very interesting topics. Thank you for doing this for us. So the questions are regarding the healthcare personalized applications. Now, you talked about the activity recognition and the speed recognition.
Mm-hmm.
Now, do you track multiple activities at the same time? For example, somebody is sleepwalking, or somebody is cross-training, or eating while sleeping or lying down, things of that sort.
Yes, so that's what, if you, first of all, thanks Nandini for your question. What you're saying that two activities at the same time, that's what I call them complex activity. So like just the running or walking is one activity, but if you are standing and eating, that is a complex activity. And what you need to do, you need to tag those activities such them. So once you are training your algorithm, you need to collect the data as a more those activity as a complex activity, so that first you need to identify what person is doing, and then you need more data to figure out what other things they are doing. So I won't say that this is two activity person is doing at the same time. I would say that person is doing one complex activity, like cooking in the kitchen, right? Some people are doing many different things at the same time in the kitchen, but I would say that this is one activity, one complex cooking activity, right?
Okay. Okay. My other question is about like the taxonomy or the activity list. Mm-hmm. Now, for some different disciplines, sometimes they have predefined lists where you can use that to customize or create your own. Mm-hmm. So for yours, did you have, so you had to do activity by body parts versus the location, humidity, lighting, intensity, and so on. So was there like a predefined library list of these are the sets of activities, and these are supposed to be the safe activities considered safe, and these are considered unsafe?
So yes, that's an interesting question. And you define your activities based on your clients or based on your problem, right? So for an example, if I want to know if my parents in India are doing day-to-day activity good or not, I just want to know if they are eating good or not, if they are doing exercise every day or not, or if they are sleeping well or not, right? So that's the one set of activity I will design for them in this purpose. But for other activity, if I say, if there is a mental hospital or psychiatric facility where I know that people try to kill themselves because they are frustrated. So for that, I want to know that if the person is trying to hang themselves, if the person is more agitated anytime, so then I will design those activity. And another example, if I know that for a football, if the person is playing football, I want to know how many times they are kicking the football, how many times are they simply running, or how many times they are jumping back and forth. So I would say that there is no generic application, I would say, can happen, but we can design customized application based on that, because somewhere I read that there are more than 2,000 possible activities a person can do using their hands and legs. So identifying those 2000 activities, I would say that all general activities would be very difficult, but identifying sort of 30, 40, or 50 activities very particular about any domain, that's very possible. And this is very, I would say that can be very accurate.
Thank you.
Yeah, no problem.
I'll ask a question, Pratul.
Mm-hmm.
In slide 12, you mentioned about generating simulated data.
Mm-hmm.
So
Okay.
did you use any software, or what was your how was the simulated data generated? Sorry if I missed that.
No. Let me go.
Yeah, I think in this slide.
We didn't use software. When I say the simulated data, basically the person were asked to do the activity. So for an example, if we are trying to collect the activity for going upstairs, we asked all our participants. So we had 19 activities for in-home activities, right? So we created two applications. One application was going on the watch, and the another application was on the phone. So the data was coming from the watch and collected on the phone. And in the phone, we had devices which we had the application which was tagging those data. So for an example, if we have to take the going upstairs, we asked all our participants to go 30 seconds or 45 seconds, go upstairs and downstairs. So once we have those signals, we just tag them as a going upstairs. So we didn't do a lot of augmentation, which is very popular in especially computer vision, where you collect some data and then augment them, right? Like you change the brightness, you flip them, you rotate them. We can also do in this, but in healthcare, usually it's advised to don't do a lot of augmentation because they might give you some different effect altogether, and that might be the noise altogether. So we didn't do any programmatic augmentation or synthetic augmentation. I would say that all the data, we just ask our participants to replicate or basically to perform so that we can just collect and use them directly in the training.
Okay, that makes sense. Thanks.
Mm-hmm. Yeah, no problem. Again, if you don't have any more questions, so thanks again, Thiru, for inviting me. Hope I can also invite you in my campus or virtually sometime this semester or next, based on your availability. So
yeah, that sounds good. Thank you so much for the talk.
Yeah, no problem. It was really a pleasure to come
Okay.
and talk to you and everyone there.
All right. Thank you all very much. We'll see you guys next week.
Mm-hmm. Thank you again, and a very happy New Year again to everyone.
Thank you
Bye-bye.
all. Bye.
Thank you.
Thank you.